Good morning, my name is Felix, and in this lightning talk, I'll be presenting on neuro-inspired localization algorithm that I've been developing in collaboration with several of my colleagues at Sandia National Labs. I'd also like to take the opportunity to thank the organizers for allowing the opportunity to share this work. Let's see. There we go, I have a pointer. Okay, so to give a quick overview of the work and its motivations, the problem that we're looking at is sensor-aided localization, which is about estimating a positional fix for an agent based on its available sensor input, or stated more informally, figuring out where you are from what you see. Solutions to the localization problem has many potential applications, which are more directly related to the domain of intelligent navigation, but also more broadly to, say, problems in robotics such as SLAM. And for our approach, we're implementing a distributed algorithm that's based on neuro-inspired models of grid cells. And we apply this algorithm to a navigation-based data set. And specifically, we consider digital elevation models, which have associated methods for terrain-aided or terrain-relative navigation. To briefly go into the neural inspiration, although I'm sure many of the audience are familiar with grid cells, they're a model of how space may be represented in brain structures such as the hippocampus or entorhinal cortex, and their activity is characterized by a periodic hexagonal tiling, which can take on multiple spatial scales, orientations, and offsets. And you can see a few of the illustrations in the figures at the bottom there. Particularly relevant to our localization work is that these grid-based representations can be used to encode and decode locations. And so in the following slides, I'll provide some background context on how we adapt these grid-based representations in a more abstract computational model, as well as walk through the implementation of the model as applied to terrain-aided navigation. So to begin, we provide a simple grid-based representation over our DEM dataset from the 3D elevation program. These are a slightly different type of data than most folks may be used to, but basically it's just a raster image of elevations over latitudes and longitudes. And there's some prior work in constructing models of grid cell activation patterns. And the work from Silstedt et al. Is what we've selected to use for now. In the figures on the right here, what we see are different sample parameterizations of the equations that have been aligned and overlaid onto the terrain. And this allows us to represent a given location as a set of grid cell activations. Now, as a refinement to this, we can aggregate the grid cells into modules that share the same spatial scale and orientation, with the free parameter being the offset. Because the grid modules are periodic, this allows us to scale the offsets to phases between 0 and 2 pi. And an illustration of this is shown in the figures in the top row, where we align the offset such that the peak in activity corresponds to the desired location. And this change allows us to represent the same location information with much, much fewer parameters. As you can see in the correspondence in the figure on the bottom left, where what would have taken roughly 20,000 grid cell activations now becomes 3 sets of grid module phases. And this allows us to expand the representation to be the phase codes from thousands of distinct grid modules, as seen in the figure in the bottom right, where each dimension carries a lot more information. So for this slide, I'll be glossing over some of the steps for decoding back to a location from its phase code for now. But what I want to highlight on this slide was that there's some nice properties to using our distributed phase code representation. In particular, the location estimates are very robust to coding noise due to the redundancy gained through using multiple grid modules, and it shows graceful degradation as the noise is increased. There's also a trend where as more grid modules are used, the slower this degradation is. And so the main figure on the right here shows increasing coding noise on the horizontal axis and localization error on the vertical axis, and the figures at the bottom are sample coincidence maps with increasing coding noise. And specifically what we mean by coding noise here is the amount we perturb the exact phase code representation for a location, and what we mean by the location estimate is the intersection point on the decoded coincidence maps that have the largest magnitude. So I'm kind of highlighting those now. So given that the phase codes only go between 0 and 2 pi, we note that pushing the noise to the order of 1 radian, as shown here, is quite significant. So that was some background. We'll now move on to a walkthrough of the localization algorithm for a sample simulated trajectory in the sensor space over our terrain. So this is first done by transforming the sequence of elevation measurements onto their possible phase code candidates through what we're calling a distributed correlation. So for a single elevation measurement such as this, we find the elevation contour of all the locations on the map corresponding to that elevation, and then transform those locations through the grid module parameters onto an occupancy grid in phase space. And for illustration, the gray lines here show the path of an individual transformation from locations to phase codes. Now, as an aside, these transformations can also be computed offline, and the phase candidate representation of this map may be stored as a lookup table of binary matrices. So now we also want to estimate the phase codes from these candidates. And so for that, we'll actually need to integrate the information across multiple sensor space measurements. And to do this, we incorporate another piece of information from the trajectory, which are the relative displacements between the measurements. Here we note that a linear displacement in the original Cartesian space corresponds to a phase shift in the transformed phase space. So we can apply these shifts and align the phase candidates with respect to a reference location, such as from the final measurement. And so you can see the effect of using this displacement information in the figures in the bottom, where for a single grid module, we can estimate the phase code as the point in the point with the largest magnitude after summing the grid module's phase candidates over the trajectory. And an illustration of the phase code estimates for multiple grid modules is shown on the right here. So once we get the phase estimates, we can finally decode back to the original Cartesian space. And these are the coincidence maps that I had glossed over previously. And these are computed by summing the grid cell activation patterns at the appropriate offset specified by the estimated phase codes. So much like the phase code estimates, we may estimate the location as the point with the largest magnitude. And as the information for more grid modules are used, this location estimate becomes more and more coherent. And as a final note on this algorithm, much of the computation may be performed independently with respect to the grid modules, resulting in an embarrassingly parallel workload. That should in theory, be suitable for neuromorphic acceleration. And so in summary, I'll conclude with just a brief overview again and some future directions. This talk presented our work in developing a distributed localization algorithm inspired by grid cell models, which we applied to an elevation data set in the context of intelligent navigation. While we've gotten a lot of promising results so far, it's still a work in progress. And there's several trade-off spaces that we're actively exploring. And one of the main extensions that we're interested in is also how to learn the appropriate phase candidates directly from sensor data as opposed to from a reference map. And we have some ideas, but this would allow us to fill in the mapping part of SLAM, whereas right now we have the localization part. We're also interested in applying the algorithm to data sets, additional data sets, and integrating it with more traditional filtering methods, such as the extended Kalman filter. An example of a different data set that we've been working with is point cloud data, as shown in the bottom figures. So this presents a slightly different input paradigm with multiple simultaneous measurements around a reference location. And we've shown that our algorithm also works in this case. And I'll close with just a quick comment that it'd be great to see more adoption of navigation-based data sets and algorithms in the space of neuromorphic applications. At least with the algorithm shown here, there's several high-level characteristics that I think make it a good fit. And since I was short on time, with that, I'll be happy to take any questions. Thanks for your attention.